And so let's go with water. Do water molecules have dispersion forces?
Yeah.
Yes.
Everything does.
Everything has dispersive forces, right? London dispersive forces. If you have electrons, you've got dispersion forces. So everything has them. What about induced interactions? What does induced interactions mean?
Delta plus, delta minus.
What's that?
Delta plus, delta minus.
No, so that's dipole, right? But induced means that you get this instantaneous delta plus, delta minus, right? So just in the case of oxygen or nitrogen that we talked about, it's those short-lived dipoles that we just discussed that can be induced in the molecule. So does everything have induced interactions? Most everything does. I think if you look in the table, you can have significant amount of induced interactions because most things are pretty polarizable. Now, fluorine, other things that hold their electrons very tightly or have high electronegativity, the induced might be pretty low, but you can have induced interactions. Now, orientation interactions are depending on how these dipoles are rotated, delta minus, delta plus, delta plus, delta minus. So say you have these two dipoles interacting, or say you have two water molecules interacting like this, and now here's the orientation of those. So the orientation part refers to how these dipoles are interacting, how they're arranged with one another. So I forgot the question now. What was it?
It was just explaining.
Where do they come from? Yeah, where do they come from? So
everything, like all molecules can orient differently. Right?
yeah, and so it really depends. The orientation, the force between these molecules depends on how they're oriented. And since water has very strong dipoles, it will have strong orientational van der Waals forces because it really matters whether you have two dipoles like this or you have two dipoles like this or two dipoles like this. And so the orientation forces in water can be pretty strong. Dispersion forces also exist in water, but they're not as much of a component because the orientation force is so strong. So when I say something like hydrogen bonding is really important in the properties of water, that's telling us that the orientation forces are very important, whereas dispersion forces are not as important in the properties of water. So we can break each of these factors down in that equation for the van der Waals energy, and I can't remember what the formula is. So what's the distance dependence of all these forces?
R to the 6.
1 over r to the 6. So the energy is proportional to 1 over r to the 6, which tells us that the interaction energy gets very, very strong as the molecules are very close, but as you move them apart, the interaction energy drops off rapidly. So what's more important, these forces in the liquid phase or these forces in the gas phase?
Liquid.
Liquid phase. Why?
Because the distance in the liquid is closer than in the gas.
Exactly. So in condensed matter, right? In condensed matter, those molecules are right next to one another. And so R is very short. But in gas phase, those molecules can be very far apart. And so their forces are much weaker between one another.
Yeah,
Yes?
but doesn't that in the gas phase, that's what causes the Boyle's law, or ideal law to veer a little bit from linear, right? these forces. So when we see it like a little bit of a curve in our graph, that where that curve is, that's where we're having some of these interactions.
Yeah, exactly. So,
I mean, they may not see, but when you graph it on the curve, on the ideal, if you're trying to do an ideal Boyle's law curve, you're going to see a little bit of a curvature instead of a linear.
yeah, so remember that, yeah, those forces, so these orientation-induced and dispersion forces exist in both the gas and the liquid phase, right? But they're much more important in the liquid phase because there's no ideal liquids law, right? We have no such thing. But we do have an ideal gas law, which means you can treat most gases kind of the same with very small corrections, right? You plotted all those van der Waals equations of state, and they were just a little bit away from the ideal gas line. Liquids, we know, have much different boiling points. You know, it's very hard to explain the properties of water versus the properties of other things because the molecules are so close together and the forces are so much stronger. Yeah. So the ideal gas law, the van der Waals equation of state, gives us very small corrections from the ideal gas law. But there is no ideal liquids law because these forces are very strong because the molecules are so close together. Go ahead. Yeah.
I know on I think it was the homework that we have for Thursday. There's a question between the difference between an ionic and a covalent bond, and I know that has to do with electronegativity, but we never talked specifically with
Yeah. So it's a good time to ask questions on the homework too. So I think the question went something like, which compounds are ionic and which compounds are covalent, stuff like that. So we had like sodium chloride, we had water, we had, I don't know what else, gold. So which of these compounds are ionic, which are polar?
Water is polar. Sodium chloride is
Ionic. I guess, let me now put gold here. Hexane. Ionic. Polar. Nonpolar. How can we figure that out? Does anyone have a strategy for how to solve that? Yeah.
Can you just take the electronegativity differences, and if it's really big, it's ionic. If it's
The-
moderate, it's polar covalent. If it's small, it's non-polar covalent.
Yeah, so we didn't go over specifically what rules to determine which is ionic, which is not. But that's the strategy for solving this problem, right? So what's the electronegativity of sodium versus the electronegativity of chloride? You know, it's got to be big, right? Because this is ionic. So the electronegativity difference is big. So the electronegativity of sodium is something like 1.3, 1.5. Oh, someone's got their table.
It's here it says sodium is 0.93 and chloride is 3.16. So
0.93 and what?
3.16.
3.16. So their difference is on the order of 2.2, something like that. 2.21, something like that, right? Whereas water, so what's the electronegativity of hydrogen?
2.2.
2.2, and what's the electronegativity of oxygen?
3.44.
3.4, so the electronegativity difference there is 1.2.
Is there a range in which they fall under ionic, polar, and non-polar?
Yeah, so various books have various ranges for, if it's above 2, it's ionic. If it's, 0, so carbon versus carbon, right? So what's the electronegativity of carbon?
It's 2.55.
2.5 minus 2.5 equals 0, right? We know it's nonpolar if the electronegativity difference is 0. That's easy to see. And anything above 0 is going to be polar, but the threshold for ionic can vary. Is it 2? Is it 2.5? Something like that. And so basically what I'm looking for is that you know to go to electronegativities. And then what you pick as your cutoff really doesn't matter as long as you can justify it. You say, well, ionic solids tend to dissolve in water. We all know that sodium chloride is ionic, and so this electronegativity difference is big enough that, yeah, it's going to be an ionic solid. So I'm going to choose this as ionic. Well, water is definitely not ionic, so, in this range is going to be polar. But that's the right way to start to solve that problem, is to look at the electronegativity difference and then make your own decision on what's the right cutoff. Yeah, we didn't discuss that in class, but that's something that is a good way to think about problem-solving strategy, right? Because I might ask you, which one is polar and how do you know? And so you say, well, water's polar because I know the electronegativity difference between oxygen and hydrogen is a certain amount, but it's not all the way ionic. Or I might say that, how do you know, can you prove to me that sodium chloride is an ionic compound? You say, well, here's its electronegativity difference, and that's high enough. So you won't have to look up your own electronegativities on the exam. I will give them to you in the problem if you need them. So don't worry about having a periodic table with electronegativities. Yeah. Worry about having a periodic table with row 1, row 2, row 3, row 4. That's the most important part of the periodic table. I saw some hands.
So
Yeah.
if difference is bigger than 0, it means that molecule is polar?
Yes. Yeah. So any difference greater than 0 is polar. If the electronegativity difference is 0, what does that mean?
Same non-polar.
Yeah, it's the same element, right? So nitrogen, oxygen, fluorine, all of those things, hydrogen, are nonpolar. So anything greater than 0 has to have a little polar character to it. Yeah.
Is there a great difference between the distance of the particles in ionic and molecular bonds?
That's a good question. So is there a difference? The question was, is there a difference in the bond distance between NaCl and HO? So what's the bond distance here versus the bond distance here? It really depends on exactly what the elements are. So say you have, and it's hard to make generalizations because these are different elements and it's different set of bonds, right? But let's say you have sodium chloride versus cesium chloride. Which has a greater bond distance here?
Cesium chloride.
Cesium chloride.